All right, so pressure altitude. This is the first altimeter reading that's not our true altitude that we're going to take a look at. And what it essentially does is it informs the pilot of the difference between the pressure at their given altitude and the standard pressure that you would expect at that location. So as we said, if you're 1,000 feet above the ground, you're going to take 1 inch of mercury off of your standard of 29.92. So you would expect 28.92. However, if certain weather systems have changed the air and pressure is higher or lower than expected, we want to take that into account. You're not always going to get the standard pressure wherever you expect. So in general, if the pressure altitude is lower than true altitude, the aircraft performance will be. I want you to think about this for a second and try and figure out if the performance will be better or worse. So the pressure altitude being lower than true altitude, it means your plane essentially thinks that it's flying lower where the pressure is normally lower. Where the pressure is normally higher. So if the pressure altitude is lower than true altitude, your plane thinks it's actually below where it actually is, which means it's going to perform better because generally the further down, closer to the surface of the Earth you go, you get higher quality, higher air density air. So your true altitude is higher than pressure altitude, meaning your plane is higher than it actually thinks it is. It thinks it's at a lower altitude where performance is typically better. So the higher pressure, at that quote unquote lower altitude that it thinks it's at is a higher density, which means the engines generate more thrust. So to look at this mathematically, we can put it all together with a few equations. You will be given these equations, but you do have to know what the variables represent. So to calculate the density altitude, which is dA, we take the pressure altitude, which I'll show you how to calculate in a second, and we're going to add that to 120 times the difference between the outside air temperature, whatever the temperature is outside of my plane, and the international standard atmosphere temperature at that location. So what's the actual temperature versus what would I expect it based on our international standard model? The density altitude accounts for pressure and temperature differences, which is why you see both pressure altitude and the outside air temperature in this problem. All right, so the first thing we need to do is we're going to have to calculate the pressure altitude. So this is the equation for pressure altitude. You're going to take 29.92, which is the standard pressure at sea level. You're going to subtract what we call the barometric pressure. That's just the pressure that you measure outside the aircraft using the aircraft's instruments. And if you remember, that standard rate of change was 1 inch per 1,000 feet. So that's why the 1,000 appears. You're going to multiply that pressure difference by 1,000, and then you're going to add it to whatever your elevation is. Just to highlight, this is the pressure at your current location. This is that standard 1 inch of mercury per 1,000 feet. And this is just the additional elevation or the additional altitude above sea level. So if you took off from sea level, your additional altitude would be 0. You wouldn't add anything. But if you did take off from some height that was above sea level, you just have to realize that you have to account for that. So what you see kind of in this kind of maroon magenta type color is the first part of that, the 1,000 feet above where you took off. And the teal color is just showing that if you do take off above sea level, you have to add in that additional height. Even though you already were there when you took off, we can't ignore the fact that all of this is relative to sea level. All right, so here's example 1, and I'll walk you through the calculations. You're taking off from an airport that is located 1,800 meters above sea level, and the barometric pressure, meaning the pressure outside the aircraft, is 30.13 inches of mercury. The temperature outside of the aircraft is 18 degrees Celsius. We want to calculate the density altitude. So we know that the density altitude can be found using this equation. So step 1 is always going to be to calculate the pressure altitude. So we're going to go ahead and we're going to use our pressure altitude equation. And our pressure altitude equation is going to take our 29.92. I'm going to subtract the pressure, the barometric pressure, which the problem gave to me as 30.13. And we were told that the altitude or the starting elevation of this airport was 1,800. So all I do is I plug in the pressure reading as well as the elevation. And this is going to give me 1,590 feet. So the plane is going to perform as if it was at that location. Just as a side note, you're actually at 1,800. The pressure altitude is lower, so your plane actually thinks it's lower in the atmosphere than it actually is. That's generally where you find higher quality air. Based on pressure alone, this plane will perform better because it thinks it's actually flying lower, because it's basically some lower altitude air, which is generally higher quality, was forced upwards into higher altitudes. But the plane doesn't know that. As far as the plane's concerned, it's no different than if it dropped to 1,590 feet on a normal day and is now flying in higher quality air. So again, you're going to have multiple altitude readings in your aircraft. If you're in the cockpit, you'll see in this case that the true altitude reading is 1,800. That's literally how far you are from sea level. But the pressure altitude tells you that you are flying in higher pressure air, meaning your plane thinks it's a little bit lower. So you know from that difference that you are flying in higher quality air. The next step after we have our pressure altitude of 1590 is to calculate the international standard atmosphere temperature at the pressure altitude that you're currently at. So if you remember, the standard change of temperature is 2 degrees per 1,000 feet in altitude. So all you do is to calculate the ISA, the International Standard Atmospheric Temperature. You take the 2 degrees per 1,000 feet and you simply multiply it by the pressure altitude, which we calculated in part 1. So that will give us 3.18 degrees Celsius, and then we have to adjust from our standard. We know the standard at sea level is 15 degrees Celsius. So what I need to do is I need to subtract the 3.18 that I got based on my previous calculation. So what that means is the standard temperature at my current location is 11.82 degrees Celsius. We would expect kind of it to be about 11.82 degrees. All right, so the problem here is the pressure altitude accounts for pressure, but does not take into account any changes in density due to temperature. And likewise, the ISA temperature calculation accounts for the temperature differences, but does not account for the pressure. And that's where our density altitude calculation comes in. It has both the pressure altitude and the adjusted temperature calculation in it. So I'm going to use that equation up top, plug in the 1590 for my pressure altitude. The problem gave me an outside air temperature at the airport of 18 degrees, and the 11.82 degrees Celsius is basically our adjustment from standard, which I calculated in part 2. And we can figure out here that the density altitude is 2,331.6 feet when I combine everything together. Now the problem told us that the aircraft was flying at 1,800 feet. The density altitude is higher than that. So this plane is actually believes that it's flying at a higher altitude, which means that the efficiency is going to be lower. It's actually not going to fly as efficiently as it would otherwise, because the plane thinks, when you account for the pressure and temperature differences, it thinks it's at 2,300 feet when it's actually at 1,800. So because your plane thinks it's flying higher than it is, we say that it's actually flying in lower quality air, because it's air that's normally further up, which has a lower air density. In our second example, we are going to take a look at a similar problem. An airport is located 4,142 feet above sea level. The barometric pressure is 30.40 inches of mercury. The air temperature is 32 degrees, and we are tasked with finding the density altitude. Step 1, as always, is to calculate the pressure altitude. So we're going to go ahead and we're going to plug in both the barometric pressure, the 30.4 inches of mercury, as well as the starting elevation of 4,142 feet. And when I plug all that in, we get the pressure altitude of 3,662 feet. The next step is going to be to account for temperature. A bit simpler, I'm going to take that ratio, 2 degrees Celsius per 1,000 feet, and multiply it by the pressure altitude that I just got. So we figure out by what factor my temperature can be expected to change. So we're going to subtract that from the standard to get our ISA temperature at that location. Once we have those two, it is just a matter of combining everything. So we take my pressure altitude, add 120 times the difference between the outside air temperature, which the problem told us was 32, and the ISA temperature adjustment, which was the 7.68. And I get a final density altitude of 6,580.4. Once again, because our true altitude is 4,142, and the density altitude, the plane, the altitude the plane thinks that it's at is much higher, we know once again this plane is going to be performing less efficiently, probably going to burn more fuel because it thinks it's flying about 2,400 feet above where it actually is. So it is actually in lower quality air. There's one last additional way